Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar lecture theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Screen recording enabled. Friends, welcome to the 29th lecture in the sequel of environmental loads. Here we will talk about return period for ice loads and other loads in detail. Welcome to lecture 29 of Maritime Structures course offered in SwayamPrabha by the Department of Maritime Engineering at IIT Gandhinagar. In the last lecture we discussed about the importance of return period. So we know the importance of return period. And we also understood how return period is connected to the service life of the structure, and we also understood how return period can also be connected to the risk estimate in the design. Now, in this lecture, we extend this concept to study something on ice loads. Ice loads are dominant in in Arctic regions. It is important to understand first this ice loads prediction is lot of uncertainties. Various ice conditions exist in Arctic region. These ice conditions prevail during the lifetime of the structure. Let us see what are they. We can have something called level ice, broken ice, ice ridges and icebergs. These are different ice conditions actually. Let us ask a question immediately, what effect ice would cause on structures? It can cause effect of creep, it can cause cracking, it can also induce buckling, it can result in spalling, and it can also cause crushing. Ice loads exist in many forms. Ice loads exhibit random variations in both space and time. So, therefore, ice loads are classified in two groups. One, total load or otherwise called as global load. The other one is local load or otherwise called as pressure. Now, global loads affect overall motion and stability of the maritime structure. Whereas local loads affect the members of the structure at specific cross sections, maybe at connections, etc. Having said this, we can now say ice load or ice force can result in a periodic motion or periodic, we can say, loading, and it can cause dynamic amplification to structures. Most importantly and uniquely, ice loads depend on the shape of the structure which they are attacking. It is seen in the literature that structures or structures with conical shape. Attract lesser ice loads in comparison to cylindrical structures. What is the main reason? The main reason of reduction of force on conical structure is a well designed cone can change the ice failure mode from crushing into bending. And we all know flexible structures resist bending better than crushing. Ice force is computed using a spectrum which is applied on to a conical structure. The example application was taken in Gulf of Ojai. We write down the equation for ice force spectrum. Before that, the ice force spectrum is based on field data. Therefore, it has lot of empirical constants. So, mainly ice force depends on two parameters: ice velocity and ice thickness. Both these quantities in the spectrum are assumed to be Rayleigh distribution. And log normal distribution. So, let us write down these equations. The probability of distribution of velocity is taken as this equation which I am writing. Probability of distribution of ice thickness is given by this equation These are available in different detailed literature. Please look at the references cited in the course for more details on these discussions. Okay? Now, let us ask a question: what is the equation governs this ice force spectrum? The ice force spectrum is given by this equation which is on the screen now. It is T bar, okay, it is not minus, it is T bar to the power of 0.64. Please write it carefully. Now, let us see what are these values. F naught is given by another equation, which F naught is here, given by another equation C sigma F H square d by L C of 0.34, where C is constant, because I said it is empirical relationship, this is taken as 3.7. Sigma F is the bending strength of ice, which is taken as 0.7 megapascal. H is the thickness of ice. D is the diameter of the ice cone. LC is the characteristic length of ice, which is given by the characteristic length of ice given by EHQ by 12 G rho W raised to the power 0.25, where E is the ice elastic modulus, which is taken as 0.5 gigapascal, and of course rho W is density of water, and G is acceleration due to gravity, which is 9.81 meter per second square. So, friends, the equation which governs the spectrum of ice is available on the screen here, where T bar, I will write down here, where T bar is called as ice period, which is computed as LB by velocity, where LB is called ice breaking length, and of course V is the velocity with which ice is moving. Let us look at this equation. F is the frequency of ice, which can be computed. So, F naught, T bar, F are all known to me, and F naught is given by here, and in this sigma F is known, H is ice thickness, D is the diameter of the cone, and LC is given here. So, friends, if I know this, I can plot the ice spectrum, which is then can be used to compute the ice force acting on structures in Arctic region. Now, let us ask a question: what are the effects of ice loads on maritime structures, especially in Arctic regions? So, we can say ice loads cause ice induced vibrations These ice induced vibration can result in fatigue failure of tubular members, It can also cause acceleration on the deck. So, the acceleration probability on the deck is given by this equation, where sigma A is given as integral S u double dot f df. S u double dot is the power spectral density of the acceleration response function that is generated as an outcome of the ice load on the maritime structure in Arctic region. Therefore, friends, ice load is one serious concern which is on specific kind of platforms, but this can be now computed using the ice spectrum given by us. The next concern what we have is the seismic load. Maritime structures which are fixed base or having stiff connections with the seabed can be candidates of vulnerability affected by seismic loads. If you take an example of a tension platform which is not fixed to the seabed, but connected to tethers, and tethers are anchored to the seabed, even this can be also affected by earthquake loads. Let us see how. Let us take a TLP. The tethers, connecting them to the seabed. Water level is here. We know that this is the water depth which we operate. So, now this seabed is forced to have some seismic signal. One may ask a question, when the platform is not directly resting on the seabed, what would be the effect of the seismic effects on the structure? It is a good question. Remember that, friends, these tethers are all pre-tension, and TLP has a condition that W and buoyancy are not balanced. W and buoyancy are not balanced. W is acting downward. This should be added to the forces of the tethers acting downward, that is equivalent to the buoyancy force acting upward, right. So, now if the seismic load is affecting the seabed and the seabed starts displacing vertically, this will now affect. So, I can now write displacement of seabed in the vertical direction affects the initial tension on the teethers. Let us say this is initial tension on the teethers, it is affected, and this in turn affects the heave motion of TLP. So, sea quakes or earthquakes in sea can also have indirect effects on floating structures or compliant structures, and of course, direct effects on platforms resting on the seabed. Let us say I have a jacket structure resting on the seabed and subjected to sea quakes. These legs are directly affected by the seabed motion. So, this is a direct effect. If I have a TLP where teethers are resting on the seabed, and if it is subjected to some seismic effect, they have indirect effect. So, both ways earthquakes in seabed affect the response of a superstructure. Okay. Now, the earthquake acceleration in sea exhibits a random characteristic. It is due to 1. Nature of the mechanism causing earthquake, 2. Wave propagation, 3. Reflection, and 4. Deflection. Next question comes, what effect earthquake can cause on maritime structures? 1. The inertia forces due to acceleration of the seabed can have direct and indirect effect on structures in sea. Secondly, the damping force due to motion of water particles caused by earthquake can also have influence on the maritime structures. So, again there are no direct measurements of earthquakes on seabed causing influence on the superstructure as a case study, but if you look at an example of a TLP, the dynamic tether tension variation caused by the vertical motion of seabed is given by this equation, which is the AE by L is axial stiffness x of t minus xg of t. So, this delta t, which is the tether tension variation, updates the stiffness matrix of TLP. Please see the reference listed of my papers on TLPs. So, in this equation x of t is the instantaneous displacement TLP, whereas x g of t is the ground displacement caused by the earthquake. So, therefore, friends, if you look at the force vector caused by earthquake on TLP in 6 degrees of freedom, the earthquake gets transferred in surge motion, in heave motion, only. Okay. So, this is simulated by artificial power spectral density function given by Kanei-Tajimi spectrum. The spectrum is given as what you see on the screen, omega g to the power 4 plus 4 zeta g square, omega g square and omega square, omega g square minus omega square of square plus 4 zeta g square omega g square omega square multiplied by S naught, where S naught is given as 2 zeta g sigma g square by pi omega g 1 plus 4 zeta g square. So, in this equation S0 is said as intensity of excitation. Omega g is the natural frequency of the ground, here in this case the seabed. Okay. Zeta g is the damping of the ground motion. Sigma g square is the variance of the ground acceleration. So, now 3 parameters which govern the spectrum are intensity of earthquake, natural ground frequency and damping of the ground motion. The above 3 parameters are estimated for representing the earthquake records by statistical estimation process. Just for example, an earthquake occurred in Gulf of Mexico approximately 250 miles west of Anna Maria, Florida, on 10th September 2006 at 14:56:07 at coordinated universal time. It was epicenter at 26.3 north and 86.57 west. The interesting part is Mars TLP operating in the Mississippi Canyon block, which is also located in Gulf of Mexico, is very close to this epicenter. Okay. So, 3 parameters were estimated based on the Karnaitajimi spectrum. There is a very interesting paper which I think you should refer by B and Gaurav, which I am writing it here. Offshore triangular TLPs under earthquake motion. Ship and offshore structures, journal. It is 33-178-184. Please have a look at this paper for more detail about how this was mathematically modeled and how expressions were obtained in the Karnaitajimi spectrum to derive the input of the ground motion effect on the mass TLP study. So, friends, we are able to now come to a summary of these loads acting on maritime structures, starting from wave loads, wind loads, current load, impact load, ice load, fire load, earthquake load, and of course, the conventional dead load, live load, and other imposed loads. Friends, it is very interesting, and you will realize that maritime structures are one of its kind where almost all environmental loads are focused to act upon, and therefore, it gives you a very large preview of loads attempting to influence the behavior of maritime structures compared to all other types of structures exist in the world. So, I want you to look into the additional references which we cited for our information. Let us quickly talk about the information on live loads, impact loads on maritime structures for our information. Live loads actually are acting on the equipments. They include the effect caused by the impacts, dynamic amplification factor is applied to compute the additional effect caused by the live loads Live loads otherwise are also designated as factored load, and load factor multiplier is used to compute them as a static load. Okay. Let us quickly see the typical values of live loads which are used in maritime structures. So, I should now say typical live load factors. Let us talk about this table of uniform distributed load on beams and deck slabs, concentrated load on deck slabs, and concentrated load on beams. If you talk about specific element like walkway, staircase, etc., UDL is given as 4.79 kilonewton per square meter, whereas concentrated load is taken as 4.38 kilonewton and 4.75 kilonewton respectively. If you talk about deck areas exceeding 40 square meter, then the intensity is taken as 3.11 kilonewton per square meter and there are no concentrated loads. If you talk about deck area of lighter use, then the load here is taken as indicated. So, one can look into the additional references cited in this course for knowing more detail about this. Let us talk about the impact loads which are considered for analysis of maritime structures. If under operation of a crane, drop objects create an impact, then the live loads are multiplied by an impact factor to account for these impacts. Let us see what is this factor. So, I now say impact factor for live loads if it is rated loading on cranes, then I divide this into two parts, horizontal load and vertical load. So, horizontal is only 20% effect, vertically it is 100% effect on cranes. If we talk about drilling hook and loads caused by that, then there are no impact factors. If we talk about hooks or cranes supporting light machinery, then the vertical loads are enhanced by 20%. If we talk about hooks supporting rotating machinery, then you have 50% weightage on both horizontal and vertical. If we talk about impact load caused by boat landing, then it is specific value 890 kilonewton and 890 kilonewton. If we talk about UDL on deck of offshore platforms, we say it is 11.975 kilonewton per square meter. On the drilling rig area, it is 71.85 kilonewton on square meter on the derrick area, and it is 47.9 kilonewton per square meter on the pipe rack, power plant, living, accommodation area. So, area wise live load is classified on the deck of the platform. So, friends, we already discussed more in detail about the types of loads acting on the platforms and maritime structures. With this lecture sequel, we complete the environmental load applications on maritime structures before we move on to the next topic, where we will touch about some dynamic aspects, then construction pre-service analysis of maritime structures for your information. So, thank you very much for patiently listening to the lecture on environmental loads, the last sequel, where we discussed about in detail the impact effects, ice loads and earthquake loads on maritime structures. Thank you very much. Have a good day. Namaste.